Okay, all right, let's get started. So today we're going to talk about induction motors, which is basically the last thing we're going to cover in class. But before going into induction motors and going into detail about that, so a reminder that the final is next Tuesday, right? And the last homework is due this Friday. Okay, so we'll have some extra office hours. So both the TAs will have 1 hour, an extra office hour, and I will have an extra office hour on Friday. So you can find those information in an email that was sent out. Again, so the final will be very much like the midterm. The exam will be released in the morning. You have the whole day to do it. It's due at midnight. And during the exam hours from 2 to 4, there will be an office hour where you can come up and ask questions. So any questions there, issues with the final? Okay, all right, so that's a final. And if you look at the grading of the class, right? So we'll drop the lowest homework. I think we had 8 or 9 in the class. We'll drop basically we'll grade sort of the N-1 homework that will make your grade highest, the homework score highest. So those, the subset of N-1 that will make your homework grade, the highest will be including the final grade calculations, right? Then that together with the lab, together with midterm and the final will be your final grade. And I will post, what your final grade in GPA will be late next week. If you have you can take a look at that. If you have questions, you can let me know. After that, the grades will be final and be submitted to the university. Any concerns, issues there? Okay, so also there is a course evaluation, right? I think it's live right now for this class. So please do the course evaluation. So we do take those, pretty seriously, right? All the feedback are, taken pretty seriously, is read fairly closely, of course, by me, but also by folks in the department who's in charge of teaching, right? So hopefully, we won't be doing Zoom's classes ever again, but whatever comments you have, you think is useful, you can leave there, right? If there are some things that you want us to keep, once we return to in person, you can leave those there. Okay? So please do the evaluation do the course evaluation if you have time. Okay? So anything else you guys want to talk about before we do induction motors and finish the class? Okay, all right, so let's look at induction motors. Again, that's sort of the last thing we'll cover. So induction motor is another type or another so there are 2 common types of electric machines. One is synchronous motor or synchronous generator, which we covered. The second is induction motor. So if you look at the synchronous generator, right, it can also run as a motor if you reverse everything. Okay, so you can run it as a motor or a generator. If you run as a generator, then the angle, sine, theta, that angle is positive. If you want to run as a motor, make the angle negative, you can put power into the machine. So that works equally well as a generator machine. So induction is another type. So can you think of, so we want to talk about the advantages of induction motors. So can you think of some disadvantages of synchronous motors? Why don't we just use synchronous motors for everything? So why bother with us creating another type of motor? Right? So why might you not want to use synchronous motor for everything out there? Okay, so one thing, if you look at the synchronous motor, that these are synchronous machines are fairly complicated because you need an exciter to, get voltage, right? So their advantage is you can control voltage in synchronous motors, but their disadvantage is in some sense you have to do it. You have to control voltage. There's many moving parts. It's sort of expensive and sort of not, that reliable. You cannot drag it through sand and expect still to work. Whereas the induction motor are extremely reliable and cheap, basically. When we have induction motors, what we have is these are reliable. These are very cheap motors. These are inexpensive in most circumstances. And they have a sort of high power weight ratio. So given the same amount of weight, you can get a lot of power out of induction motors. And so induction motors are, so for generators, most times we use synchronous generators because you have the, so you want to, have the option of controlling a lot of things. But for motors, a lot of time we use induction motors because these are sort of cheap, simple to build, very reliable, not much can go wrong inside induction motor. So these are nice things of induction motor. So the way you make an induction machine is actually quite simple. Okay? The way we make an induction machine is quite simple. So think of induction machine and think of you have three-phase power coming into it. Okay? So when you have sinusoidal three-phase power, what happens is you have a flux. Right? You generate some flux inside the stator. You generate this flux. So once you generate this flux, then you have a flux that sort of rotates with time. Basically, this flux rotates inside the stator and does sort of 1 revolutions per cycle of AC supply. And this flux is called air gap flux because it's sort of within the air gap of the stator. Then you can compute what the speed of the rotating flux is, right? Because the flux makes 1 revolution per AC cycle. So then if you look at the rotational speed of the flux, this sort of rotating magnetic field, magnetic flux, then we have the number in revolutions per second is basically the frequency. And then in revolutions per minute is 60 times the frequency in RPM. When we talk about RPM, we have 60 times the frequency. So when you just build a stator, so imagine all you do is you take the stator and you put three-phase power into it. You provide sinusoidal current, and this sets up this flux inside the stator. Right. So if you look at this synchronous speed, so for our system, how fast is this in S? Let's say 60F. How fast is this in per RPM terms? For our system, what's the RPM? If it's 60 times F?
3,600.
3,600, right? So this is for us, this is 3,600. Is 3,600 fast or slow? Do most things rotate at 3,600 RPM?
Really fast.
Right, 3,600 RPM is very fast. If you think of motor rotating at 3,600 RPM, you probably don't want to go very near this motor. Okay, so this is a synchronous speed. So how do you slow this down? Any ideas of how do we slow this down? So I have this 3600 RPM as this very fast rotation speed. Right? You have a mechanical machine, you may want to rotate a little bit slower. Right? So you have a motor with your washing machine, maybe not 3600 RPM, right? Maybe not that speed. So how do you slow this down?
You lower down the frequency.
That is not possible, right? 60 Hertz is not changing for us.
Oh, so the 60 hertz is gonna stay constant.
Oh yeah, 60 Hertz is never changing for us. At least in the AC system, we're never tell a power engineer change from 60 Hertz, right? So if you go to a job interview, you say, oh, can you change 60 Hertz? You probably get, they will stop it right on the spot. So alpha AC signal is 60 Hertz. That is given, but how do you slow the rotation speed of the machine?
You could have more changes in polarity per revolution.
Right. So the idea is just to, right, instead of having one rotation of the flux per AC cycle, you can have half a rotation per flux in AC cycle. The way you do it is basically adding more poles. And what a pole means is just sort of this one phase of a three-phase power system. So before, remember, we had A, and let's say what happened to A prime, right? And A1 prime. We only had this pair. Now let's adding more poles. Okay? Let's also adding A2, and let's say A2 prime. So what you do is you have the wire, let's say for phase A. Okay? Instead of just connecting it to say AA prime, you connect to both A1, A1 prime, A2, A2 prime. And the impact of this is, if you do this, then when the AC cycle, when you undergo one AC cycle, the flux actually, you don't see one complete revolution. You see sort of half the revolution because you finish with AA1 prime, but you haven't finished the sort of the revolution respect to AA2 prime. Okay, so if you do this, instead of one revolution in one AC cycle, you get half a revolution in one AC cycle. So your speed goes from 3600 RPM to 1800 RPM, right? So this is the way we slow down the speed. This is the way to slow down the speed. So the way to read it is if each phase has one coil, this is called a two-pole machine. The word two-pole machine comes from that, you have A and A prime phase, right? So there's two poles on this. So that rotates, one complete revolution per AC cycle. Have two coils, meaning you have A1, A1 prime, A2, A2 prime. This rotates, 180 degrees per AC cycle. So this is called a four-pole machine. And so the more poles you have, the slower the flux rotates inside the stator. The air gap flux has a slower rotation speed. Any questions? Yeah, go ahead.
Yeah, like a limit numbers of poles that you can add on.
So that's mostly sort of physical engineering feasible, how many wires can put into this. That mostly comes from that. There is not a mathematical limit, but just sort of, hardware-wise, how many can you put on?
Thank you.
So you have machines with, a lot of poles, like 100 poles. You do have machines with that, right? If they need to spin very slow, you can have 100 poles. There's large machine with large number of poles. But most commonly you'll see are this sort of 4-8, sort of 12 poles machines, okay? So this gives us the way to slow it down, and the equation is fairly simple. So the equation is fairly simple. Is if you look at your synchronous speed, right? This is 60F divided by something called PP. PP stands for pole pairs. Okay, so what we have is there's two poles. goes to 1 pole pair, 4 poles, goes to 2 pole pairs, things like that. So if you want to directly talk about in terms of poles, you have 120 F over P, and this is just the number of poles we have. And this is in the units of revolutions per minute, or RPM. So this is, so as you increase the number of poles, you have a slower speed. So these are the equations written out. Okay. And these are the, for example, the pictures of motors. Basically, you have a rotor shaft. So what you do is you have wires coming in at these points. These are the different sort of poles on the machine. So you have wires coming in, you apply the AC power, and then the rotor shaft starts to spin. So these are the machines, and they're incredibly easy to make and incredibly robust machines. Okay, so not much can go wrong in this kind of machines. So you have, squirrel cage rotors, and these are used, at a lot of places where you need a simple motor. So the way this works is quite simple. It's basically, what you do is you apply a 3-phase voltage on the stator windings. You apply this voltage. And this creates a rotating magnetic flux. Right? So what your rotor does is this rotor sees the magnetic flux. So if you, let's say this is your 3-phase power coming in here. And then what you do is you have a rotor, and this rotor, what it does is you have a wire that's in short circuit. Okay. So if you have flux, if you have magnetic flux, this causes some current flow on the wires. Then this current flow on the wires, what it's trying to do is we'll try to line up the magnetic field you see in this wire with the rotating magnetic field that's outside of it. So what this does is now this tries to make the rotor rotate. And that's what generates a torque in the rotor. And thus you can convert this to mechanical power. Okay. So really this is sort of application of Faraday's law, right? A magnetic field, if you have a wire in a magnetic field, there will be current on the wire. And then this interaction between the current and the outside field is such that the field seen the magnetic field on this current on this wire will be the same as the outside field, and this creates a torque on the rotor itself. And this is torque that drives the rotation of the rotor. So if we want to be more, let's be more rigorous about this, then we can write down Faraday's laws. So what Faraday's law says is the following. Faraday's law says this is the voltage this is the flux density. This is the length of the wire. And what this V is the speed of the wire that moves respect to the magnetic field. So once you have a non-zero speed, so if the magnetic field is moving with respect to the wire, or the wire is moving with respect to the magnetic field, then this creates a voltage, or voltage creates this movement. And this in turn creates a force. Because what happens is now, since you have a voltage, this generates a current, and then this generates a force. Okay? So a wire in a magnetic field will try to move. Right? So a wire will try to move such that it lines up with the magnetic field and sort of have the same speed as magnetic field. So this is Faraday's law. And then there is a rotational sort of analogy to Faraday's law. right? So Faraday's law is what basically you have magnets moving. So here we have a rotational analogy as the voltage. You generate some voltage. Then this is related to the relative rotation speed. Okay, so this is relative rotation speed. You can generate this voltage. And then this in turn leads to a torque. This in turn leads to a torque. So one thing we can understand this as, let's say this is your stator. And you have some magnetic field rotating this way. And then if your rotor is rotating, let's say a little bit slower than the outside magnetic field, then this delta n, then the speed difference in rotation will result in a torque on the rotor, because the rotor will try to go faster, let's say catch up with the outside rotating magnetic field. So this is how the torque is generated. Basically, you have the rotor trying to always catch up to the reference field that's generated by the AC sinusoids. Any questions for this?
Is the rotor a magnet?
Rotor is not a magnet, but it's a shorter wire. You can think of it that way.
Okay, sure.
It's a wire that's shorter. Other questions?
I think I kind of get the concept, but I think if I think it's gonna, for me, it's kind of gonna need like a lot of like seeing things like visually and hands-on.
So hands-on, we won't get to it, but we'll try to give you some equations with this. Seeing it a little bit hard, so I'm going to try to give you some conceptual ideas of how this works. Hands-on, hopefully we can do more hands-on stuff in the future. So let's look at the conceptually, a little bit more conceptual idea. Right? So let's start with the starting point. So let's say you have a motor that's not connected to anything. Again, let's say you have a motor that's not connected to anything. So obviously nothing is spinning in this motor. So rotor at a standstill. Okay. Then I connect the wires and I apply a three-phase voltage to the stator. So then this provides us with a air gap flux that rotates at synchronous speed. Okay, that rotates at synchronous speed. Then what happens for your rotor is rotor winding. So these are the wires in the rotors. What they see is, hey, they see a flux going through at synchronous speed. Okay, they see this flux going at synchronous speed. And then this induces a current in the rotor winding. Right? So they see some field passing by, this induces current. So what would the current try to do? Let's say your rotor, you're standing still, but outside of it, right, you have this sort of field that's rotating at synchronous speed. Then what you try to do is you try to catch up to this speed. Okay? You try to catch up to this field that's rotating at 3600, let's say RPM, or some synchronous speed. Right? Then this creates a torque, because now the rotor wants to turn, right? Wants to turn at the synchronous speed to catch up with it. So then the rotor rotates, and then you catch up at the synchronous speed. Okay? Then you catch up to the synchronous speed. Right? So basically, what the rotor wants to do is wants to minimize the difference between its own speed and synchronous speed. So the way it does that is basically rotate at the synchronous speed. Right? It wants to rotate at the synchronous speed. So once that stands still, you need some power to make sure the rotor starts. You need some starting torque to make sure the rotor starts to turn. And then once it gets to synchronous speed, actually it doesn't take any more torque for the rotor to work. Because once it's at synchronous speed, then what the rotor sees is a constant flux, because everything is at the same speed. So since a constant flux, there's no voltage, there's no current interaction, and there's no torque anymore, right? So torque is created when there is a speed difference between the rotor and the synchronous speed. Any questions about this sequence? Right, so the most important concept to remember is you create torque when you are different than the synchronous speed. Okay, so the larger the difference between the rotor speed and the synchronous speed, the larger the torque is, because the rotor will try to catch up to the field, to the synchronous speed field. Right, so that's the basic operating principle of the induction motor. As you somehow generate this field, and then the rotor tries to catch up to this. So basically what you have is, this is your synchronous speed, right? This is the rotor speed. This is the rotor speed. And because there's a difference, if delta n is not 0, then I can support some torque. Okay, so my speed difference is proportional to the torque I want to generate in the system. And so this is what I want in the system. Okay, any questions about this picture?
Professor, can I ask a question?
Yeah, go ahead.
So what if the speed are the same? The rotor will suddenly like stop, or it will like continue to spin for a while.
The speed being the same.
Yeah, I mean, when the speed is the same, so the torque will be 0, right?
So the torque is 0 and the rotor spins at the same speed as the synchronous speed.
Oh, okay. So it will continuously spin at the synchronous speed.
Right. Because the frame of reference for us is the synchronous speed.
Okay, so it will rotate at the synchronous speed, but there's no torque.
There's no torque, right?
Okay,
There's no torque. There is only a torque if you are different than our frame of reference, right? So remember, our frame of reference is the synchronous speed as generated by this AC voltage is applied to the state.
Okay, I
so
see.
when your rotor is right, so we talk about difference in speed. We're not talking about a rotor, so that's sort of absolutely standing still, because that doesn't, right? So for that, we're not referencing to that. Our reference is actually to the external synchronous speed that's being generated. So the bigger the speed difference, the higher the torque. Exactly the same speed difference, no torque.
Okay, I see. Thank you.
Okay. Any other questions? So this is the important picture having in mind. Right, let's see.
So you said so it's the speed different, like the inner speeds, not the rotor. The rotor stay the same, stay still.
And the rotor doesn't stay still, right? The rotor, the speed difference is the rotation speed of the rotor, this n. So this is how fast the rotor spins. The synchronous speed is the speed that's generated by the flux.
Oh,
Right? By the fact that I have an AC voltage coming into the stator. So that's a flux speed.
and then when the flux speeds and the rotor speeds are the same, then there's no torque.
There's no torque, right? Then the system is then the speed difference is 0 because it's the same speed. The rotor is the same speed as the reference, as the synchronous speed.
And then it's become equilibrium.
Yeah, that's equilibrium.
Thank you.
All right. So this is so you generate torque by having a speed difference, right? So if you want more torque, then your rotor will create a larger speed difference. If you have one less torque, will be a smaller speed difference. Okay, so it's a difference in the speed between the synchronous speed and the rotor speed that generates a torque in the system. So this motivates us to have a definition called slip. The reason we want to define slip is because, right, fundamentally we care about, this value. Slip is just a normalized version of this value. Okay, so slip is this delta n normalized respect to ns. So this is ns minus n over ns. Okay, so this is the slip. So the slip being 0 means the rotor speed is the same as the synchronous speed, right? So slip being large means the rotor speed is very different than the synchronous speed. So most of our equations will be in terms of this slip s. And so this is a very convenient number to use, right? This is sort of a fraction that tells us how fast we are normalized by synchronous speed. So slip is really the variable that shows up in our equations. So slip is defined in many ways. It's the difference in synchronous speed over the difference in speed over the synchronous speed. This is also, of course, you can convert this to say radians per second if you want, right? You can convert this. Sometimes our equations are given radians per second. So this is these are all equivalent when you define slip. Right? So if you look at in radians per second, then this is the rotational speed in radians per second instead of in RPM. All right, so S is really a variable that shows up quite a bit. Right? So for example, one straightforward example we have is, let's say you have a 2-pole 60 Hz induction motor operating a slip of 0.02, compute the rotor speed. Right? So we want this as meaning that find n, right? Find n in RPM. So the first thing to do for all these calculations is to figure out what the synchronous speed is. Right? So this is 120 frequency divided by the number of poles. This is a 2-pole machine, 3600 RPM. S is ns minus n over ns equal to 0.02. So n is 28 RPM. Right, so this is a sort of simple way. This is sort of a very typical question. Right, so typically you can be given the speed, find s, or given the s, find the speed, things like this. So if you look at this type of question, there are basically only a few synchronous speed that can happen, right? So for example, if you look at speed in 60 Hertz, right? So it's 2 poles, 3600, 4-pole 118, 100, 1800, 1200, 900, 720. So these are there are sort of discrete synchronous frequencies we can have in the system. Okay. So if whenever you're doing some computation and you get a number that's very different than some of these, then you made a mistake. For example, there's no way to get a machine with a synchronous speed of say 2000 RPM. Okay, that's just not, we cannot get that machine. Okay, there's no way to get that machine. Right? Any questions about synchronous speeds? So what if in practice you actually want something that goes, that's not as close to the synchronous speed? So let's say in practice, what if you want something that goes at let's say again 2000 RPM? What do you do? Right? So you basically, if you need that, you need a gearbox. Right, you need a gearbox to do to change speeds. But a lot of times when you try to design something that's close to the synchronous speed to not use a gearbox. Okay, so if you look at some applications, you will wonder, why there's something at 900 RPM was so special about 900 is basically it's easy to make. I can make a pole machine that goes at 900. All right. So because there are only few distinct values, right? So it's it's common to ask this type of questions. It's fair game to ask these questions. So this says the steady state speed at 60 hertz is of a motor is 1150 RPM. Find the number of poles and the slip. Okay, so the way you look at this is, so if the steady state speed is 1150 RPM, then how many poles does it have if you look at this table?
Six poles.
6 poles, right? So if you look at this, it has to be 6 poles. Right? So this gives you a synchronous speed of 1200 RPM. It cannot be others. And then S is an S. This turns out to 0417. And the idea for this, so how do we tell, right? How can we tell? This is 6 poles, right? Why is it not 4 poles, but with a very large slip? So normally, so for a motor, S is positive. Okay? I need a positive S because I'm consuming power. Okay. Then S is normally less than, say, 0.1. S is typically fairly small. Okay? So if you look at this table, if you have something, say if you have more poles, let's say you have 8 or 10 poles, then S will be negative. That doesn't make sense for a motor. If you pick something like 1800, then compute the slip. Slip will be very large. This also doesn't happen in practice. Okay, so normally if you look at S, some positive number, some small positive number. So if you do a question, you get a negative S, or you get an S that's something like 1 on the order of magnitude of 1 or 0.5, then that's where you probably made a mistake in your calculations. Right, so slip are typically not very large, okay? Or slip are typically fairly small. Questions? Okay, so this is the sort of intuition behind the induction machines. So next, let's look at the equivalent circuit, right? Because what we care about is doing power, voltage, and current calculations. So we want to know what the equivalent circuit is. So what turns out what the equivalent circuit looks like is our equivalent circuit basically looks like a transformer. The reason it looks like a transformer is the following. If you look at the rotor, what happens is we have this kind of windings, and they are basically shorted. Okay? If you have a rotor, the rotor is shorted, and we have windings coming together. This is 3-phase. Okay? Then when you have windings, so rotor has windings. Of course, when you look at the stator, each of the phase still has all have windings on them. So A, B, and C all have some windings associated with it. So this is basically, you have 2 pairs of windings that's magnetically coupled. Right? You're coupled through the flux, the air gap flux, and you have this sort of windings. And this basically results in a transformer. Okay, what this looks like from a circuit perspective or electrically, this looks pretty much as a transformer. Okay? You have some windings on both sides, so that gives you the N1 to N2 ratio. Okay, there's some turns ratio. Then we have, on the stator side, we have the primary input of a transformer. On the rotor side, you have the secondary of a transformer. Right? So this, you can think of this rotor as a transformer, where instead of using a metal core, we're going to use air gap core. Okay, we just have air gaps. And this air gap creates this sort of transformer action. So right, so now we're shorting the where we don't have an output on the rotor, but so let's just short it, and this is what the diagram looks like electrically. Any questions with this model electrically? Okay, so that's just the induction motor just made of these two parts. The stator looks like the primary side of the transformer. And then the rotor looks like a secondary. Okay, this thing just looks like a secondary side of the transformer. Right? So once you have a transformer, then we can use all our equations. Okay, we can assume, all our equations. And to make things easy, we'll make the assumption that n is less than ns, and thus this is a positive number. Okay, so once the rotor starts to rotate, we'll assume that it's still consuming power in its rotation. So this is still a motor instead of a generator. So then if I have some rotation in the motor, then our question is, now if things start to rotate, then where does the fact that you're rotating show up? Right, so a little bit the non-trivial part of this is if it starts to rotate, then where does this rotation show up? What changes in the circuit that reflect different rotation speed? Right, so you want to think about is we have different slips. Where does the value of S enter if I start to rotate? Any ideas? Where does S come in once my rotor starts to rotate?
Does it have to do with the voltage on the left?
Does it impact things on the left or on the right? Right, it impacts the secondary side because the left side is the stator. The stator is getting some AC voltage, right? So the stator doesn't care what S is, has no impact on the AC voltage it sees, right? It's getting this AC voltage. So what impacts is enters the secondary side. Okay, so S enters here. Okay, so let's see how S enters here. It doesn't change not quite the inductance. What happens is it changes actually the resistance here. So let's look at how does S enter here. Okay. All right, so S has no impact on the primary side. The stator doesn't care, but the rotor cares what S is, right? Because right, the non-zero S, meaning you're generating torque. Okay, so that has to show up. So the way it works is basically, if you have a flux that rotates at delta n, what impacts is basically impact this induced voltage at the rotor. And what ends up doing is this rotor gets impacted. Okay, so this E2 gets impacted. This voltage that you see gets impacted here. Okay, this is impacting the voltage. And when the rotor rotates, the way this voltage impact shows up is, right? So the amount of voltage I see, right? This is proportional to S, right? To this delta n. Okay, so right, so I take it back. Yeah, so this S does impact inductance. Yeah, I was wrong. So this S does take impact inductance. So what happens is once you have this once you have this sort of voltage, and then your field is changing proportional to S, that's your speed difference. Then basically what you have is change the magnitude of the voltage and the frequency of the voltage. Okay. So both impact the magnitude and the frequency because you have this rotating flux, and depending on your speed difference between your rotor speed and the synchronous speed, this flux changes, right? This sort of the effective flux you see changes. So then if you look at this relationship, as let's think about, right? So let's say I have E2. This is the voltage at NS, right? So if I'm rotating at NS, I see this number E2. Now let's say I'm at, right? So now if you want to talk about, we can talk about, let's think about this. So this is actually, yeah, so voltage, so let's talk about this, right? So let's say if rotor is at standstill, so this is not moving. This is N is 0. Then you have a large voltage. You have a large voltage at E2. So here E2 is proportional roughly to the synchronous speed. Okay, so this is proportional to NS minus N, which is just NS because I'm standstill. Now, as you move faster and faster, if the rotor is at speed N, then the voltage you see, this is roughly proportional to delta N. Now, this is NS minus N. Okay, so it's roughly proportional to this. So the ratio of different voltage you see on the secondary side, this is NS minus N over NS, same as slip. So the voltage you see on the secondary side is S times the voltage you would have seen for a rotor that was standing still. Okay, for a rotor that was standing still. Right, so if this is a little bit confusing, then I guess remember the fact that is if your rotor was not moving and you have synchronous speed, and you experience a lot of torque, a lot of voltage, right? You try to catch up very fast, so you have a high voltage. As you get closer and closer to synchronous speed, your voltage drops lower and lower, right? Your voltage goes down because you see less torque, you see less voltage. So the way this changes is this is proportional to S. Okay, so when S is 0, meaning there's no speed difference, then the voltage you see at secondary is essentially 0 because there's no torque. There's no power generated. Okay. So this is the equation we have. This is sort of is proportional to E2, and this proportion, sort of the constant of proportionality is this S. Okay. So this is similar for frequency, actually. Similar for frequency is if you're at standstill, the frequency is an S. If you're at speed N, your frequency is proportional to this delta N, the changing frequency. So what we have is we have this frequency is, once you're rotating at speed N, your frequency is the slip times the frequency you will see as standstill. Okay. So then what we can write is the following. When we have, right, so when we have this circuit, basically this number is changing and this number is changing as function of slip, as a function of slip. Okay. So if you look at induced voltage, then both induced voltage and induced frequency changes. And this frequency, XR, You want this is 2 pi times the frequency times the inductance. So you can pull S out of this. This is 2 pi times F times inductance. So this S times some X2. Whereas the X2 you can think of as the actual value, reactance of the inductor. And once the rotor gets spinning, this is modified by a factor of S. And this is modified by a factor of S. Right, so now if you look at this equation, the interesting thing is the following. As in this picture, we have this depends on S. Right, so this is a number that depends on the slip. This is a number that depends on S. What we want to do is instead of 2 of them depend on S, what we want to do is we want to turn this, we want to put this S by this R2. Okay, we want to pull the S away from ER and XR and put it into R2. And we can do this because of following. If you look at the current flow through this is ER over R2 plus J XR. So we're going to multiply and divide S at the same time. Okay, so we're going to multiply S. We're going to multiply and divide S at the same time. So this is SE2 R2 plus J. So this is SX2. Okay. So divide S from the numerator and the denominator at the same time. This is E2 over R2 over S plus JX2. Okay. So equivalently, we have a circuit where instead of the voltage and the reactance depending on S, we have the resistance depending on S. Okay, so this is how we are going to think of the equivalent circuit. So we're basically, we'll have a transformer circuit where we'll put S into the resistance on the rotor side. And then our full circuit representation is this is a transformer, except the R2, the resistance load, the resistance depend on the step S. Okay, so this is our equivalent circuit. So what S shows up is S will show up to the value of this R2 number. Okay, S will show up in this R2 over S number. All right, so let's test whether this makes sense. Let's test this whether this makes sense. Okay. So let's say when S is 0, what happens? Remember, when S is 0, your rotor is spinning at the same speed as the synchronous speed. So that'll give you a slip of 0. Then R2 over S is basically infinity. And does that make sense? So if S is equal to 0, R2S is infinity, do I have any current flow on the secondary side? Are there current flow in this circuit?
No.
No, right? There's no current flow because this is open. This is essentially open circuit. No current flow means I'm not generating any power, right? No current flow, current being 0 means power is 0 because V times I is 0. So that makes sense, right? S being 0 means that there's no, S being 0 means there's no current flow, there's no power being generated. So the largest S can be as 1, right? That means your motor starting at a standstill. Then you recover the original circuit where you have R2. And you do generate power because you have non-zero current, and this kicks, right? And this is the power that kicks the motor into starting. This is why the motor will start to spin. Okay, so this is the equivalent circuit picture we'll have. So most of the questions will be, figure out what S is, plug S into here, compute the power and the current. Right? So once you have this equivalent circuit, then all the calculations are fairly straightforward. Right? Any questions on this equivalent circuit? So this is the circuit to remember, actually. This is the circuit you want to remember. Okay, so if not, let's take our break. We'll come back and at 3:37, and we'll do some numerical calculations with this equivalent circuit. Okay, so we'll pause now, resume at 3:37. All right, let's get started again. All right, so this is our equivalent circuit. But this circuit still have a transformer inside of it. All right, so as we do for transformers is refer all the parameters to the stator, right, by defining this prime. So we have R2 prime, I2 prime, X2 prime. Once you do that, then we don't need to draw the transformer anymore. We can just, eliminate transformer by referring things to the rotor. So we have this equivalent circuit. And there's one more thing we can do to this circuit to make things, to rearrange things and make things better, easier for us. And the thing we do here is we can use the equation, the fact that R2 prime over S, this is always equal to R2 prime plus R2 prime S1 minus S. And so this is always true. You can just add them together and you can figure out this is true. But the nice thing about writing R2 prime over S this way is now if you look at the circuit, what we have is we have X2 prime here. We still have R2 prime here. And we have R2 prime S1 minus S. Okay. So the nice thing is I can separate out this resistor, R2 prime over S, into two parts. And then once I do this in two parts, what happens is I can interpret each part of the circuit easier. It's easier to interpret. Right? Because I have something that's corresponding to the primary winding side of the transformer, something to do with secondary side, still R2 prime, X2 prime. Then the load, all the load that shows up, everything that depends on S shows up in this one place. Okay, so you can imagine if S is non-zero, what it creates is it creates a resistor. The load electrically shows up as something with a resistance. That's R2 prime over S times 1 minus S. Okay, so all the impact of the fact that you have an induction motor and you have this slip S, everything just shows up at this one place. When you take a transformer, a induction motor is basically this transformer with some load. Right? This load is R2 prime over S times 1 minus S. Any questions with this? Okay, so this is all it is, right? So, think of induction motor as just transformer with a variable load. And this variable load depends on S. And then the next thing we want to do in this motor is we want to basically figure out where does the power go, okay, right? So, right, so I'm powering this load, I'm powering this motor load. So where does the power go? Well, one way to think of where the power goes is let's do a power accounting from the left to the right, okay? From the left to the right. So what I have is first I have input power. Right? My input power is P 3 V times I1 cosine theta. Okay, so this is my input power, right? This is what power my source is giving 8. Then we're interested in how much power make it to the air gap. Basically, what we're interested in is how much power does it make here? Does it go from the primary to the secondary? Well, you can lose power in two places, right? You have a stator copper loss. This is PCU1, 3I1 squared R1. right? So you can lose power through this resistor. You can lose some power here. You can lose some power through this resistor. So we have, the core loss square times R. So this is how much power we have. Then after the loss, this goes into the air gap. So we have something called air gap power, PG. This is basically 3 times, right? So this is the power that's consumed by the load resistor by the resistors on the right-hand side. Okay. Right, so I have I squared prime going through R2 prime and R2 prime over S. Right, so this is how much power I have on the air gap. So anybody remember how to relate power to torque? Then if this is the power I have to the air gap, then how much torque do I generate? Right, so this, by power, I mean this, you have the stator here, you have the rotor, right? So at this point, I have power PG, right? But then I want to know how much torque I generate, right? Because often the motor is, rotating in terms of torque. So how do I relate power to torque? Multiplied by rotation speed, right? So power is the torque multiplied by the rotation speed. Right? So I have some airfield flux going at omega s. So this is omega, right? So this is my torque. Okay? So my TD, this is my developed torque. Right? So this is the amount of torque I have after the losses on the stator side. So this is my developed torque. So of course, this is not all air gap power make it into the load, right? So this is PD is developed power. This is 3I2 squared R2 over S1 minus S, right? Because some power is lost in the rotor, right? So I have some loss, Cu2, this is 3I2 squared R2. So after this loss, I have a developed power. And here I have PD equals to TD times omega, right? Because my rotor is rotating, slightly slower than the synchronous speed, right? So the torque depends on basically. So when I multiply by the rotational speed, this is omega, the actual speed of the rotor. So this then is divided to the output power. Okay, so this is P out equals T times omega. You have some losses. These are, for example, the rotational losses. So this is the loss in the gearbox. This is the losses in the mechanical rotor, things like this. Okay. So this is the power flow picture. As you go from left to right, you lose power in R1, Rm, R2, and then finally you deliver power to the load, which is R2 prime over S times 1 minus S. Okay, so this is the chart for power flow. Any questions for this power flow? This power flow chart? Okay, so this is our flow chart, and most of the questions basically is about this chart. Okay, so almost all the problems for induction motor has to do with finding a branch on this chart or finding a box on this chart, and doing some calculations. So for example, let's do this question. Let's say I have 60 Hz 3-phase induction motor, right? That produces 100 horsepower. So this is my output power, right? So this is my output power at this RPM. Then my rotation losses are 1.2 kilowatts. The stator and copper and core losses are 2.1 kilowatts. I want to compute how much power I'm actually sending into the machine and the efficiency. Okay, so this is what we want to do. All right. So the way you do it, it's basically you're given this number, right? And you try to climb up this tree basically to figure out the input power. And then if you have the input and output power, you can figure out the efficiency of the motor. Okay. So for this problem, the way to sort of go up the tree is the following, right? So let's first convert horsepower to watts. So 1 horsepower is about 750 watts. Okay. So then the next time we go up the tree is we know the rotational losses. We know the output power, so we can add them to get the developed power. Okay. We can get the developed power. So the developed power is the output power plus the power you lost in your rotations. So this is some 4 plus 2, some 5.8 kilowatts. Okay, this is our plot. So next we want to go up a chain again. We want to go to air gap power. So we know the developed power is 1 minus S times air gap power, or the air gap power, developed power divided by 1 minus S. So if we know S, we can figure out what the air gap power is. Then we can go up again to find the input power. So here it doesn't give you the number of poles, right? It just says this induction machine runs at 1150 RPM. But then what is an S in this case? What is the synchronous speed if you're rotating at 1150? Even without knowing the number of poles?
$1,200.
1200, right? So this is, so your speed is not very different than the synchronous speed. So the synchronous speed has to be 1200. So we get a slip of 0.0417. The air gap power is PD minus over 1 minus S. When the input power is the air gap power plus the power you lost on the stator side, as this is also given. So we have, this is 81.2 kilowatts. The efficiency is just the output power of the input power. And we get this is about 91.88% efficient. Okay, so this is our, this is sort of often our problem will look pretty much something like this. Any questions? This. Okay, so so this is a chart you should know well, or you should know where to find it. And most of the time you're doing something with this chart, with this tree. Okay? You're either going up the tree or going down the tree, or going from one block to another block. Okay, so this is the tree diagram to look at. Okay. And we can draw a lot of, right? So remember our original circuit? We can basically, the circuit we want to look at as just a simplified circuit. Okay. So what we want to look at is we want to move the shunt to be in front of the circuit, because once we move the shunt to be in front of the other elements, then the voltage is the same on both sides of this shunt. We'll combine the reactance and resistance together, and we'll just draw this load. So here XEQ is X1 plus X2 prime, REQ is R1 plus R2 prime. And then the developed resistance is RD equals to R2 prime S1 minus S. Okay, so often we'll just go with this circuit. Right? Often we'll just go with this circuit. We won't bother with the full circuit from before. And once we have this circuit, the equations become fairly simple to write down. Because once the circuit looks like this, you can write down the magnitude of the current fairly easily. Right? Because this voltage is V, also on this side. Then we have sort of some inductors and some resistors. So the current is V over the square root of this expression. So remember the complex current is V over R1 plus R2 prime over S plus J XEQ. So if you want to figure out the magnitude, then you square, right? You take the the magnitude is given by taking a square root of the real and the imaginary term squared, respectively. Okay, so this is I2 prime. So this gives us an idea of current. Then with this current, we can pretty much get to power and the voltage. Okay? We can get to power and torque. Okay? Because since we know the current, then the torque in the system is just the power divided by the frequency. Power is basically, right, current magnitude squared times R2 prime S1 minus S. So if you write this entire thing out, we get 3V squared R2 prime 1 minus S over S omega. Okay, so this is our developed torque. This is our developed torque. And the reason we want this developed torque is because now we want to understand, for a given S, how large is the torque? Right? For a given S, how large is the torque? So for a given, we can plot this thing. We can plot this TD. So this is basically TD. This is the slip S. So here we have the speed. So at this synchronous speed S equal to 0, the torque is also equal to 0. Right? So we said, when there's no speed difference, you don't generate any torque. And then the rest of the curve, you can plot the curve, there's some maximum. Then sort of slowly decreases once it gets to, so this is a starting torque, right? So when the speed is 0, you have some starting torque. As the speed ramps up, torque increases to a maximum, then comes down back to 0 when the synchronous speed is 0. Right, so you can turn this around. You can draw it like this if you flip it around. Right, so you want torque on the x-axis, you can draw speed on the y-axis. So both ways are fairly common. And for here, we have a starting torque, a max torque, and speed. All right, and the way that it works is we have some torque that's demanded by the load, right? So the load depends on torque. For example, if you have a water pump, it will demand some torque at a certain speed. So that's a green line. Then you cross it with a torque speed curve, and thus you figure out this is the slip you should operate at. And again, the important thing is to remember is that you normally operate at a fairly small torque. Sorry, fairly small slip. We operate at a slip that's fairly close to there. Any questions with this torque speed?
Can you go back up?
Sure.
False line. Another one. Yeah, can you explain this graph a little bit?
Oh, so this is just a graph
Okay.
drawn on its side. Like this is literally if you just flip the XY axis.
Oh, you just
So
flipped
if
it.
you look at this graph, you tilt your head, it looks something like this.
So for the x-axis, it's both the slip and the speed increasing.
No, right? So let's
Oh,
look at this picture, for example. Let's look at this one. The speed is increasing, the slip is decreasing, right? Remember, the slip is ns minus n over ns. So the speed increases if n gets larger, s gets smaller. Right? So at the synchronous speed, we're operating at zero slip.
oh, I see. Yes, that I just confused with the arrows at the bottom
Yeah.
because there's just two axes. Yeah, it's from 1 to 0. I see.
Yeah.
Thank you.
Okay, right. So this is a torque speed characteristic. So the important thing to remember is basically you are operating close to a synchronous speed. Right? So you operate the normally the slip is small, right? So less than 0.1 or 0.2 that you operate at. So of course we can sort of compute, right? So since we have a maximum, we may just well figure out what this maximum is, right? What the value corresponding to this maximum is. So it's fairly simple as you write down the torque equation. You take a derivative with respect to the slip. And then what you figure out is the maximum torque occurs at this S max, and the maximum torque is given by this equation. Okay, so really not much to it. It's just you take a derivative, set it to 0, and these are the equation that pops up. So it turns out the maximum torque is given by this for R2 prime over square root of R1 squared plus X2 squared. You plug this into the torque equation, you get the maximum torque. Okay, so often if we design a motor, we want to know what is the maximum torque this motor can provide. And this equation tells us what the maximum torque is. And this is basically limited by your motor rating, right? This V square is your motor rating of the motor. The larger the motor rating, the larger maximum torque. Omega S is really is also depend number of poles. Right? So it depends on your synchronous speed, so number of poles you have in your motor. It also then depends on sort of the R1, R and X parameters in the rotor. Okay. Sorry, depend on the R and X parameters in the motor itself. All right, so then let's do sort of the one last question, and this question basically has every part of it, right? This question has everything inside of it. So this question says, let's say we're given this motor with all these parameters. This is input voltage, frequency, number of poles, right? So, and say, okay, at some load, my motor speed is this, and then find all these things, right? From slip to the losses, to the maximum torque, to the current at maximum torque. So this is the question we'll see, you'll see most of the equations in play, right? So let's just go through all these questions, right? So the first thing for almost all questions is if you want to compute the synchronous speed, right? So you can eyeball the synchronous speed pretty easily as 1800 RPM. If you want to be more systematic, you can use equations. Equation of frequency over number of poles, 60 over 4. This is also equal to 1800 RPM. And the slip is ns minus n over ns. And then we get a slip of 0.0222. Okay, so this is our slip. We want to compute the developed torque, right? So developed torque for us is we have all these equations, Okay. So remember the developed torque equation. Once we plug things in, this is 3v squared R2 prime divided by S omega S R1 plus X equivalent squared. This is our equation for the developed torque. Omega S, we can compute. This is 2 pi over 60 times the synchronous speed. This gives 188.5 radians per second. So you plug everything into the equation above, you get the torque as 121.56 Newton meters, right? So this is our torque equation. Now this asks for the developed power. Well, if you look at our block diagram, right, so the developed power is the developed torque times the frequency, omega, right? The frequency you're spinning at. So you can go back to here and say the frequency is 2 pi over 60 times the rotational speed. So a bit slower than the synchronous frequency, 180. This is 184.3 radians per second. Then the power as a developed torque times its frequency, we get this as 22.4 kilowatts. Okay. Then we asked to find the current. The current, we had the equation for this. This is V over R2 over S squared plus X equals squared. This is 29.1 amps. This is our current. Then we're asked to find the loss, right? We're finding the copper loss of the motor. So the losses are just 3 times the current times the resistance. This is 1.27 kilowatts. Okay, so this is the loss. Then we want to find the maximum slip, speed, max torque, and the current max torque. So we use the equation we just seen. This is the maximum occurs at R1 squared plus X equivalent squared. This is 0.0989. So even the maximum slip is not very large. The speed is 0.98 RPM. The max torque, you plug into the max torque equation. R1 plus R1. Newton meters. And then of course the current is the exact same formula as above, where S is replaced by S max. So we get 90.4 amps. Okay, so I know this is sort of a long question, but you want to study this problem because this sort of involves, most of the equations you see for induction motors. Okay. And then just a word for the final exam and for the homework is most questions involves just looking at this chart. Okay, so when you see an induction motor problem, right, don't panic. Read the question, figure out which box in this tree you're looking at, and just use the equations here. Okay, just use the equations here. Any questions?
Yeah, could you explain how you found the current at max torque?
Sure. So current at max torque is basically this equation with S replaced by S max.
Okay, got it. Thank you.
So just that one.
Okay.
Right. So any other questions?
Same equation, just use the S max instead of S.
Yeah, same equation. So this equation is always correct. And just now we're asking for the current at maximum slip as a slip that gives the max torque. So it just substitute this S max into it.
Okay.
Okay, any other questions?
Can you go back to like really top slides when you start talking about the currents? I think it's
This
like
one?
even above the graph, like those like foregraph at the a little bit
Current.
the currents.
So this is the torque speed.
Little bit
Like
more.
this current, this one, the
Yeah.
current.
Like
Okay.
I understand that I is just over equivalent of R, but for this part, like I kind of confused where the square roots come from.
Oh, okay. So this so you understand this complex number, this equation, right? Right. So for the complex current, it's V over the total impedance, which is R1 plus R2 prime over S plus JX equivalent, right?
Oh, I see. I got it.
Yeah. So then take the magnitude of this.
It basically the magnitude of both the complex.
Yeah. This is, right. So you take the magnitude of the numerator as a denominator as in the form of A plus JB. So you get this square root.
I see. Thank you.
Any other things? Okay, so if not, then this is the end of the quarter, right? So thanks for sticking this class all the way through, and good luck on the final next Tuesday. All right, so see you guys then.
Thank you so much, Professor.
Thank you for a great quarter.
Yes, thank you for the quarter, Professor.
Thank you for the quarter, Professor.
Thank you.